Hi Bobcats. In this video we'll take a look at the relationship between kinetics and equilibrium. The main connection that I want to look at is the connection between a catalyst and equilibrium. If you'll remember back from the chapter on kinetics, if you add a catalyst to a reaction, it provides an alternate pathway for the reaction to take place, an alternate mechanism. And that alternate mechanism has a lower activation energy, but here's the deal. You end up in the same place. You just end up there faster. So if you look in the second graph at time on the horizontal axis and the concentration of B on the vertical axis, you'll see that for our uncatalyzed reaction, which is the one in purple, it versus our catalyzed reaction, which is the one in green, they both arrive at the same equilibrium value for the concentration of B, which is our product. It's just that the green one gets there faster. The catalyzed one will go faster, but it will arrive at the exact same equilibrium position as the uncatalyzed reaction. So here were all of our learning goals from the chapter. We needed to define and explain the condition of equilibrium. That's where we were using terms like dynamic equilibrium. The reactions continually keep happening. It's just at an equal rate in the forward direction and the reverse direction. We wanted to determine equilibrium expressions and constants. So that's where we learned to write that K is equal to the products raised to their coefficients divided by the reactants raised to their coefficients. And if you have more than one reactant or more than one product, you just keep multiplying them in the top or in the bottom. We looked at using equilibrium expressions as formulas. We usually have a number for K, and then we'll be given enough information about all the other chemicals that we can solve for one unknown. We also saw how you manipulate these equilibrium expressions based on changes to the chemical equation. If you multiply all of the coefficients by a constant, you raise the equilibrium constant value to that same constant. If you reverse the reaction, you take the reciprocal of K. And if you add two reactions, you multiply their Ks. We took a look at the reaction quotient. The only difference between Q and K is that you can calculate Q at any time. You can only call it K if the reaction is actually at equilibrium. If Q is bigger than K, that means you have too many products, so the reaction will go in the reverse direction to reach equilibrium. If Q is smaller than K, then you don't have enough products, and so it'll go in the forward direction to reach equilibrium. We looked at ice tables, which are a very powerful tool to track the stoichiometry of the reaction when it's in equilibrium. And then we also looked, for this last bullet point, at Le Chatelier's principle to see how we can change something like the temperature and how that affects the equilibrium.